Good day everyone, this is Rizal Jean B. Pangan. So today we will discuss about binomial by Poisson. We define the binomial discrete density function with parameters n and p as n taken x times p to the power of x times the quantity of 1 minus p to the power of n minus x for x equal to 0 up to n. So if the parameter n approaches infinity and p approaches to 0 in such a way that np remains constant, say equal to lambda, then n taken x times p to the power of x times the quantity of 1 minus p to the power of n minus x approaches to e to the negative lambda times lambda to the power of x all over x factorial. And this is just the function of Poisson distribution. Note that our parameter np is just equal to lambda. So our p is just equal to lambda over n. For our proof, we have n taken x times p to the power of x times 1 minus p to the power of n minus x, which is just equal to n taken x. Since our p is just equal to lambda over n, so we have lambda over n to the power of x times 1 minus lambda over n to the power of n minus x. So by definition, we have n factorial over x factorial times the quantity of n minus x factorial. And then just copy lambda over n to the power of x times 1 minus lambda over n to the power of n minus x. So to easily get our target, so we have lambda to the power of x from this one over x factorial from this one, and then multiply it to n factorial over the quantity of n minus x factorial times 1 over n to the x. So this is just equal to this one if you multiply this, and just copy the 1 minus lambda over n to the power of n minus. So next, just copy lambda to the power of x over x factorial and just multiply these two. We have n factorial all over n to the x times n minus x factorial, and just copy this one, 1 minus lambda over n to the power of n minus x. So after this, we have now copy this lambda to the power of x over x factorial. Then now let us expand this one, this term. So we have n times n minus 1 times the quantity of n minus 2 up to n minus x plus 1 n minus x all over n minus x factorial times n to the power of x. Then just copy this one, 1 minus lambda over n to the power of n equal to lambda to the power of x over x factorial times the expansion of this one, which is this one, and then just copy this. Next, we have lambda to the power of x over x factorial. So as you can see, we can cancel this out. So we only have n over n times n minus 1 over n minus 2 over n times n minus x plus 1 all over n, and then copy 1 minus lambda over n quantity to the power of n minus x. So this is just equal to n to the x. Now we have lambda to the power of x over x factorial times, this is just equal to 1, this is just equal to 1 minus 1 over n times 1 minus 2 over n times 1 minus x plus 1 over n. And then we have 1 minus lambda over n to the power of n times 1 minus lambda over n quantity to the power of negative x. We just separate these two. And this, so we will now get the limit of 1 minus 1 over n times 1 minus 2 over n times 1 minus x plus 1 over n as n approaches infinity. And then the limit of 1 minus lambda over n to the power of n as n approaches infinity. And the last one, we have limit of 1 minus lambda over n to the power of negative x as n approaches infinity. That the limit of the harmonic series 1 over n as n approaches to infinity is equal to 0. So the limit of this series is just equal to 1. To show, we have the limit of, say, 1 minus x plus 1 over n as n approaches infinity is equal to limit of 1 as n approaches infinity minus the limit of x plus 1 over n as n approaches infinity. So, copy. Then, rewrite this one. We have limit of x over n as n approaches infinity minus limit of 1 over n as n approaches infinity. Now, we have limit of 1 minus the limit of, put the x here, 1 over n as n approaches infinity minus limit of 1 over n as n approaches infinity. So the limit of this is just equal to 1 minus x times 0, since, as we have recalled, the limit of the harmonic series 1 over n as n approaches infinity is just equal to 0 minus 0. So we have 1 minus 0. So we have 1 as the limit of the series. At the limit of 1 plus lambda x to the negative 1 quantity to the power of x as x approaches infinity is equal to e to the lambda. So to solve for the limit of this, we have the limit of 1 minus lambda over n quantity to the power of n as n approaches infinity is equal to the limit of 1 minus lambda n to the negative 1 quantity to the power of n as n approaches infinity. So this will become e to the negative lambda. This is just equal to 1. We have now lambda to the power of x over x factorial times 1 times e to the negative lambda times 1. So we have now lambda to the power of x times e to the negative lambda over x factorial, or this can be rewrite into a function of Poisson distribution. We have e to the negative lambda times lambda to the x over x factorial. Thus, for large n and small p, the binomial probability can be approximated by the Poisson probability e to the negative np np to the power of x over x factorial for lambda equals np. So for our example, we have a baker put 500 raisins into dough, mixed well, and made 100 cookies. You take a random cookie. What is the probability of finding at least 4 raisins in it? So for the solution, we have the number x is 1 cookie. In 1 cookie, I mean, is binomial with n equal to 500 and p equal to 1 over 100 or 0.01, which is the probability of getting 1 cookie. Neatly Poisson with parameters np, 500 times p 0.01, which is equal to 5, and then the probability of finding at least 4 raisins is probability of x greater than or equal to 4, which is equal to 1 minus the probability of finding 3 raisins, that is f of 3. And then by seeing the Poisson table, we have 1 minus the value of this is 0.265. So the probability of getting at least 4 raisins is 0.735.
And that is a brief introduction of binomial by Poisson. This is Rizal Jean Pangan. Thank you and God bless.